Saxon's Calculus, Lesson 105, is about the second fundamental theorem of integral calculus and the natural logarithm function. Again, on page 514, they go through their graphing, their function machines. Page 515, they're showing you the area graphed under the curve, and then at the bottom of 515, they get to the box that tells you what the second fundamental theorem of calculus is. If f is a function that is continuous on an open interval called I, and c is a number somewhere on that interval, then the function has an antiderivative, which they're calling capital F, on this interval, which can be described as, so the function for that antiderivative is f of x equals, integrate from c up to x, the original function with a t, function of time, dt. And their conclusion is that there is an x value that is an element, that's what that swooshed looking E means, is a part of, a piece of, it came from the i's, which was some number in between. Well, it didn't really give me the boundaries, but it would be a part of that I set. All right, then it concludes, since f is an antiderivative of the function, then the derivative of the antiderivative would equal f. Okay, so that's a very wordy way to basically say, if you are deriving an integration, you're undoing it. It's like add is the opposite of subtract. Exponents are the opposite of, no, not exponents. E is the opposite of natural log. 10 is the opposite of log. Multiplication undoes division. It's that same concept. Okay, so here is the simple thing from example 1. Find d over dx of the integration of from 9 to x t squared dt. Okay, so the number part is irrelevant, and I'm going to prove it to you in this first example only. So if I do this, I get 1/3 t cubed, and I'm plugging in from 9 to x. If I plug in the x, I've just changed this t value to an x value, and then 9 cubed, and 1/3 of that is 243. But then when I go to derive it, what happens to a constant when I derive it? Well, it drops off, and that takes me straight back to, if I derive that, x squared. So all I basically did was change the t to an x because that's what I was using up here. So the constant doesn't matter, they just undo themselves. So the answer here is x squared. Okay, so now that you know how simple that is, example 2 says find the derivative of the integration from x to 4, and again, that 4 is irrelevant, sine t over t. All right, so you're going to change the t's to x's because that's what's given here. And I do have to make the change of sine goes to negative, or comes from negative cosine. So that basically then inserts the negative into the problem when it goes back to being its sine. So it's negative sine x over x. Okay, let's look at example 3. D dx of the integration from 17 to x of e to the negative t squared dt. Well, since this is an e statement, I know that it keeps itself with its exponent, and we change this to an x rather than a t, and we are done. Then part B is the natural logarithm function. And so they go through again, long explanation on page 517 to get to example 4 where it says, show, using your definition of the derivative of the natural log of x, which you already know is 1 over x, that it results in the same derivative that you get when you do y equals log base a of x. Okay, so basically it's that same derive an integration of the 1, and so that goes to 1 over x, and that is what you get when you derive natural log of x. It's 1 over x. So again, you're just using this new theorem that you got to prove, and I'm like, well, isn't that pointless? You know that this undoes itself, so whatever the derivative of natural log is this answer. Anyway, but if you go through that integration, you have made that point, but I just said it's relatively pointless to have done it.